This is my first tutorial at the OHDSI. So 2 years ago, I stood in line as a waiting list to get into this room and learn about the OHDSI but it's an honor to stand in front of you all and actually give this tutorial. Fantastic. So when I came here to the OHDSI community in 2016, they were talking about the word cohort. And I'm an epidemiologist. I understand the word cohort, but the cohort is used in various different ways. And as a true scientist, I looked it up on a peer-reviewed place called Wikipedia. And Wikipedia disambiguation page came up and says cohort means a lot of things. And then I looked through it and I said, okay, probably this is the closest thing that makes sense. So cohort, there was 2 different meanings that was closest to what I understood. As an epidemiologist, I understood cohort study. I understood retrospective cohort study, prospective cohort studies, but what we mean in OHDSI, the construct of cohort is not a cohort study. It is something to do with, the closest definition on Wikipedia was a group of subjects with a common defining characteristic. The key word is common defining characteristic. And informaticians would call that as a phenotype, and epidemiologists may call it as a cohort. So this is a paper from one of our community leaders, George Hripshak, and they talk about phenotype. And I was trying to equate this to clinical understanding. So when I was in medical school, when I was a resident in internal medicine, I would do a case presentation, a bedside case presentation. I would say, this is a 55-year-old gentleman with acute onset of chest pain that radiated to the left side into his shoulder. It increased with exercise or exertion and was relieved by rest. This is a classic description of angina, a phenotype of angina. This is how clinicians think. We think about some common characteristics about a group of people. Now, wouldn't it be cool to be able to query the database for this type of phenotypes? So the formal definition of a phenotype by George Hripshak and others was, a phenotype is a specification of an observable, potentially changing state of an organism. Angina is an observable, potentially changeable state of an organism. Correct? So this phenotype, this concept of phenotype can be documented in various electronic forms. It can be documented by me going as a resident and typing in the electronic health record saying, I saw Mr. Jones who was found in bed at night and had chest pain and it was acute in onset, it was radiating to the left, and I can write a paragraph about it. Or I can pick an ICD-9 code or ICD-10 code or a SNOMED code and document that information. Depending upon the type of resource that I have access to, I document information in the electronic health record. So the idea that the description that I just said, chest pain radiating to the left arm, that can be converted into an algorithm that you can use to query a database. In OHDSI, we call this cohort definition. So by using this complex characteristics brought together and being able to query a common data model, that is our understanding of cohort definitions. Now, this is a slide that shows you how using different types of data sources can impact the way you identify your people. So each circle here represents a different type of data source. The purple color is a medication data source. The yellow color is an ICD diagnosis code-based data source. And the green color is a text note-based data source. There are various disease conditions. There is atrial fibrillation, there's Alzheimer's disease, breast cancer, and so on. And depending upon the type of data source you query, some data source seems to be giving more cases, more phenotypes, while others are less. For example, in atrial fibrillation, medication seems to be a good source for a large volume of people, and notes seems to be lesser. While for Alzheimer's disease, notes seems to be a big source, while the medications are lesser. Each data source has a motivation behind it. When I was a resident, I would type it. I used to hate putting ICD-9 codes or ICD-10 codes. I used to love typing it in because it was closer to how I thought. That was the way I would do phenotype description. OMOP-CDM is a structured common data model. There is a new tables that are coming that are called the node tables. And with node tables, we could hopefully at one point in time do annotations. And those annotations would convert the unstructured portion to a structured format. And once it's in a structured format, maybe we can tag along a SNOMED code or a RX norm code, and then we can query all of these data sources in a consistent way. So in OHDSI community, in general, there are two ways that we could query people from a database. There's a rule-based process, and there is a probabilistic process. The example that I gave you of having chest pain radiating to my left arm, having an age of around 55 years, that's a rule-based process. So you can go to Atlas and say, I want to query all the people who are 55 years of age, have had chest pain and maybe went to the emergency room and then had certain drugs. Those combination of rules, that's a rule-based cohort definition. This is the most common methodology that we use in the OHDSI to build our cohorts. Now, there's an upcoming way of doing this too. Maybe we can use some form of machine learning to build cohorts. Maybe we can build a rule-based cohort, and then we can use some algorithm, a machine learning algorithm, to predict the probability that this person has that rule-based phenotype. So there is a package, R package, that is being built. It is going to be demonstrated live, I think, on Saturday as part of the cohort tutorial, where one of the tutors will show how to build a probabilistic cohort definition. So we will focus on the rule-based cohort definition. In the rule-based cohort definition, you got to remember, OMOP Common Data Model is a person-level data set. OMOP Common Data Model captures events about people in time-stamped records. So these events are organized into domains. So if you look at that graph, that figure here, the x-axis is time. This is one person's data. X-axis is time. And then you can see various types of domains. Domains like conditions, drugs, procedures, and measurements. So this person probably had a condition of some kind, then got a drug for that condition at a later time. They may have gotten better, they may have gotten worse. They got another procedure as a follow-up of that initial progression and disease. So all of those are documented, and they are now available for rule-based phenotyping. So the various domains that we can use in the OMOP-CDM are conditions, diagnosis codes, drugs, procedures, measurements like lab results, height, observations like opinions of people. This person has this type of something, an observation. Or visits, inpatient visit, emergency room visit, pharmacy visit. So these are available as building blocks, as time-stamped events. Now, in the OMOP-CDM version 6, you have more domains that you can query off to build. If you're doing health economic analysis, you have access to the sponsor data source. So who is sponsoring the health benefit? Or if you're doing value-based, care-based analysis, you may want to know one benefit design versus another benefit design. Is there a difference? So you may want to build cohorts out of those. Or maybe you want to build cohorts based on cost categories to say, I want to compare people whose healthcare cost has been more than $100,000. So all of these are new domains that are available in OMOP-CDM 6. So going back to the idea of cohort. In OHDSI, the formalized definition of cohort is a set of persons who satisfy one or more inclusion criteria for a duration of time. And the key here is the duration of time. A phenotype was defined as an observable entity, observable attribute about a person that can change over time. So, but for a certain period of time, that phenotype was stable. It has a start date and an end date. A cohort is a subject, with a phenotype for a subject with a start date and an end date. That is the formal definition of cohort in the OHDSI ecosystem. Now, there are some rules about the cohort that we have to think about and remember. This slide is probably the most important piece of information that you want to look at, remember in all of your studies that you want to do using the OHDSI ecosystem. A person may belong to more than one cohort. A person may belong to multiple cohorts. If I have migraine and atrial fibrillation, I can belong to the cohort of atrial fibrillation, I can belong to the cohort of migraine, and I can belong to the cohort that is a combination of migraine and atrial fibrillation. So I can belong to multiple cohorts. One person may belong to the same cohort at multiple different time periods. So take the example of angina. It had a start date and an end date. Once I stopped having angina, I don't belong to that cohort anymore. But 6 months later, I may have another attack of angina or myocardial infarction. So that would have a separate start date and an end date. So I may have an episode of angina with a start date and an end date. I may have a second episode of angina with a start date and end date, and these two do not overlap. They are separate. One person may not belong to the same cohort multiple times during the same period of time. Extremely important. So two records for the same person cannot overlap. The OHDSI, if you use the OHDSI tools, they will, if you find two records for the same person with overlapping time periods, it will collapse them and make it into one. There can only be one record for a certain time period for a person. Now, one cohort may have 0 or more members. So you could have a cohort that has 0 members. So if I would query an administrative claims database to look for people who had chest pain radiating to the left arm, increased by exertion, relieved by rest, I don't have any ICD-9 or ICD-10 codes that support that type of rule. So I would have a 0 output in my administrative claims data-based query. But if I had a natural language processing and I was using some electronic health record-based stuff, that thing that I typed 10 years ago in Cerner system would be available for query, and it would say, Dr. Rao typed in this piece of information. And this is Patrick Ryan's pitch here. He always says, code set is not a cohort. Just like I've experienced the notion of somebody giving me a list of ICD-9 codes and say, build a cohort of this. No, it's more than that, because there are some rules around it. There are temporal rules. Do you want these ICD-10 codes before or after a certain event? Do you want to use, if you talk about they should have this diagnosis codes and these drug codes, do you want the drug codes to be at the same time, on the same date? Do you want it to be 10 days later? Do you want it to be 15 days before? So all these are rules that you have to take into account as part of the cohort build process. So, the OHDSI definition of cohort, we are at 12:30. I'm going to continue for a few more minutes. Is that okay? So, every person has an observation period. You cannot have records for a person outside the observation period. This is a foundational rule of the OMOP Common Data Model taught at the OMOP's CDM tutorial next room. So inside that observation period is a person's cohort start date and a cohort end date. Once your queries are done, this is how a cohort would look like. For every person, you would have a start date and an end date, a person ID, start date, and an end date. You could have person ID number 7 has 2 records, but if you notice, they do not overlap. Very important, they should not overlap. A person can start and end on the same date. One person may not belong to the same cohort multiple times during the same period of time. As you can see, there is no overlaps in any of these brackets. Extremely important. Now, to get to this table, you can write a lot of SQL. You can say, hey, I want people with chest pain. I want people with hypertension. I want people to be on a certain drug. To do that, you may want to join the table, which has called condition table, with the drug table, maybe with an observation table, and so on. And you will get a very complex query. That complex query would look something like this, or maybe even worse than that. And it's going to become a nightmare, or you can use a tool like Atlas. Atlas helps you build cohorts. So in Atlas, and this is what we will be focusing on next, is there are the rule-based, the rules are called criteria. And these criteria are used to identify those individual time-stamped events from the CDM. The rules are categorized into different types. There are entry events, inclusion criteria, exit criteria as errors, and this is where we will stop, and we'll talk about the rest after lunch. So before the break, we talked about some theoretical constructs around the OHDSI ecosystem. And these constructs are extremely important. So we talked about the cohort phenotypes, we talked about the value of different data sources, we talked about rule-based phenotyping and probabilistic phenotyping. There's a huge difference between the two. Probabilistic phenotyping is for the future, it is upcoming, it's really good. Watch out for Aphrodite, and that is probabilistic phenotyping. We talked about how the CDM contributes to the rule-based phenotyping. We talked about the different domains, the upcoming domains for rule-based phenotyping, and we talked about the construct of the cohort. We have a formalized definition for cohort, and we talked about certain rules. So I wanted to, before we go into Atlas and actually go through some cohort build process, I wanted to ask if anybody had any questions about these concepts, so if you want to do a discussion. Everybody understands the concept of a cohort? Go ahead.
So during the break, you and I talked briefly. I would have some concerns about how those cohorts are impacted by either unknown or not yet completed temporal events. We don't have an end date. We don't know the beginning date. Open time frames.
Okay. So the question is, if there is a situation where we know the start date when somebody met certain rules, and we do not know the end date when they stop meeting those rules, how do we handle that scenario?
In your engine example, we clearly know that they came in for an emergency visit, but we don't know when the cardiologist ultimately declared them outside of that event or that.
Fantastic. Okay, so let's take the angina event. So in a typical phenotype of a person suffering from angina and a potential myocardial infarction would probably come to the emergency room via an ambulance, or maybe driven by somebody else through in a private transportation. They would get some blood draw, they would get the heparin, they would get some heparin or some sort of anticoagulant to prevent progression of their MI, if there is one, and they would look for cardiac biomarkers that indicate whether there is cardiac injury. If there is no cardiac injury after serial follow-up, they would discharge the patient from home, and they would get some sort of outpatient referral, right? So if you had access to electronic health record, or if you had administrative claims database, you would probably say there is a discharge date for that person. So if you were an investigator who's got an expertise in cardiovascular studies and is interested in this particular subject, you would define a phenotype based on your understanding of that domain. And so you're the domain expert who would say, I would define this phenotype as the date of entry would be the date they got admitted to the hospital or emergency room. The date of discharge would be my cohort end date, if you're looking for the angina episode only. Now, you may have a slightly different research question, and in that question, maybe I want to know the the first 1 year after the first incidence of angina per person. So in that case, where you want to study the 1 year outcomes of people who had their initial episodes of angina, how many get a myocardial infarction, how many go to the emergency room again for chest pain, then your cohort end date would be 1 year after cohort start date, right? So depending upon your research question, you would specify the criteria for exit, criteria for entry, and anything in between. Does that make sense?
Fair.
Can you take it out of
Can I what?
It's not able to capture the full screen this way. And then
So there's another question that was asked during the break, which was, could you please elaborate on, or as a clarification, could you please elaborate on that one person cannot be in the cohort more than one time? That's actually an incorrect statement. A person can be in the cohort more than one time, but they will be in the cohort for different dates. So one person cannot be in the cohort for overlapping date ranges. So you cannot have one row record in the cohort table that has a start date and an end date for me, and you cannot have another record with a start date and end date that overlaps with each other. They can be separated out. So if you're studying, if your research question is around what happens to people during their angina-related inpatient care, then every time I go to the hospital, the date of admission will be my cohort start date. My date of discharge would be cohort end date. And every new admission with a different cohort start date and a different cohort end date would be a record in the cohort table. Okay.
Likewise with pregnancy or something like that.
Pregnancy too, correct. So this is where we left off. So after this, we'll go to Atlas. Atlas is a tool that is used for rule-based phenotyping or rule-based cohort definition. If you think about how research, scientific papers are published, and you completely generalize the framework, then let's take the example of the Graham study. The Graham study has certain inclusion criteria, certain rules that they used as part of this study. What the OHDSI community has done is taken the generalizable framework of all of these studies and created these types of criteria types. So this is a screenshot of the Atlas user interface. The Atlas user interface to build cohort has 4 sections. The sections are cohort entry events, inclusion criteria, cohort exit, and cohort errors. So if you are studying angina, or if you are studying people on a certain drug, you will have to put in certain rules for the cohort entry. Then you may want to say, I have some criteria, additional criteria that goes into the inclusion criteria. So let's formalize this a little bit. Cohort entry events. Cohort entry events are defined as CDM records, the records from the common data model, selected from a patient data that qualify the persons for presence in a cohort. So if you are studying people with angina, then maybe the condition occurrence of angina qualifies a person to enter into a cohort. The inclusion criteria, use of other patient data relative to the initial event to qualify the initial events as valid for inclusion. So if you have seen studies that show you attrition diagrams to say, we started with 15,000 people and then we excluded 20,000 people because they did not meet our age criteria. We excluded 10,000 people because they already had a drug that we did not want to confound the study. We had certain other conditions, that comorbid conditions that we did not want, like they may have had cancer or they may have had previous myocardial infarction. And these are things that we don't want our study population to have. That goes into inclusion criteria. The cohort exit is what we just talked about. It modifies how long each event persists, the patient's presence in the cohort, or identify records that censor the event. So these are important concepts. So in the example of angina, you may want to exit the person from the cohort when they get discharged from the hospital. Or you may want to exit the person 1 year after their angina. Or you may want you to exit the person when they get myocardial infarction. There may be different rules for exit, and those exit rules are represented in the cohort exit criteria. And then there is the cohort errors. This is the process of chaining. So if there are events for a person, and events is defined as something that has a start date and an end date, if there is an event for a person that overlaps with another event, Atlas will collapse them into continuous periods of time. And that continuous non-overlapping periods is the cohort definition. So there are 4 constructs in Atlas: cohort entry events. So if you think about the common data model, there are different tables. There is the visit occurrence table, the visit detail table, condition occurrence table, procedure occurrence table, drug exposure table, and so on. All of them have person-level data. Person-level, which is time-stamped by a date for certain visit concept, drug concept, or procedure concept, or condition concept. So if you pick the people who are on the drug warfarin, then you will say, I want to query all the people who have the drug concept of warfarin, and then you will get person ID, which is the person who got the drug, and a drug exposure start date. You could also get drug exposure end date. But the event is person ID and drug exposure start date. That start date is their initial event. So all of the dates that the person got the drug exposure will be part of the cohort entry event. So once you get get a temporary table that says I have a list of all the persons and their respective start dates, and if you look at a drug, you can have multiple dates that they got the drug. Each of those is an event that gets captured. Does that make sense so far with me? It's a little imagination here. So you have an entry event. Once you have the entry events, for that entry event, you can now apply criteria. For every date that the person had warfarin, you can now check to see if they have any criteria, other criteria. That criteria can be age. Did they have an age of greater than 65 on that date that they got the drug? If they don't have that, if they're less than that age, maybe we could take them out or keep them. How about diagnosis? Did they have a history of myocardial infarction before that particular date? So all of those are part of your inclusion criteria. And here's another concept here. In RDC, there is no exclusion criteria. So an exclusion criteria is the absence of an inclusion criteria. So in RDC, in Atlas, you can say presence of 0 occurrences of myocardial infarction. Presence of 0 occurrence of myocardial infarction is like saying not having myocardial infarction. So it's very logical system for inclusion criteria. There are various options for cohort exit. So one of the exits, and this is the default exit, is once somebody has a start date, their default end date is the last known date that we have data for them, the observation end date. The last known observation date for that person, last known valid observation date for that person. Now, you can also do the fixed time. So if you want to do 1 year follow-up, you could. And when you say 1 year follow-up, Atlas will look at the last date of observation end date or 1 year, and whichever is earliest, it will pick as the cohort end date. And like we talked about, there could be censoring. Censoring could be, did they stop taking warfarin? Or did they have myocardial infarction? Or maybe they switched from warfarin to another drug, and then we don't want to study them. So these are cohort exit criteria. And so on. So this is a paper that has been used historically for all analysis. Patrick went over this. Can anybody in the community, in the group, tell me what, at a high level, can you describe this paper to me, to this group? So what are the drugs being compared? Warfarin and dabigatran, perfect. So what drug is being compared to what? Is it dabigatran being compared to warfarin or warfarin being compared to dabigatran? Dabigatran compared to, so it says, we formed new user cohorts, propensity score matched, who initiated dabigatran or warfarin for the treatment of non-valvular atrial fibrillation. So one of these groups, one of these cohorts could be warfarin cohort, and the other cohort could be dabigatran cohort. So, and we are comparing the two. So one cohort is the target cohort, and other is the comparator cohort. So once you have those, then you want to study certain types of outcomes. Based on this paper, can somebody volunteer? What is the outcome that we are studying? What is the outcome cohort?
Bleeding events.
Bleeding events. So bleeding events is one of the outcomes. There actually is many outcomes. There is the outcomes like ischemic stroke, intracranial hemorrhage, major gastrointestinal bleeding, and myocardial infarction. So all of these are different types of outcomes. So when you formalize this study definition now, you have a target cohort, a comparator cohort, and several outcome cohorts. So if we are able to build rules by looking at this paper, and we are able to build rules for target cohort and comparator cohort and outcome cohort, maybe we'll get a complete study through Atlas. So this is one of the outcomes. This is the outcomes that was pre-specified, and this here at the bottom shows you your favorite ICD-9 codes for ischemic strokes. And obviously, if you have a data source that does not have ICD-9 codes, then what do? You can't execute this study because you don't have ICD-9 codes. You could crosswalk it to something else and standardize your data source and then use something like SNOMED. That's what Atlas does. So if you have a European data set that does not use ICD-9 codes and you standardize it with SNOMED, you could probably translate this to and use this study. So let's go to Atlas. So Atlas has certain options here. We are looking at cohort definitions.
Quick question.
Yeah.
I guess for point of clarification, that paper. How about now? All right. That paper was not necessarily done using OMA. You're using it as a reference to see how others could build a comparative cohort.
Right. Right.
Sorry if I only missed that.
Right. The paper is used as an example of the type of health outcomes research studies that are being done, and is one of the examples of what Atlas would support. So what I've picked here is if you go to the URL that we gave on amazingawsdemos.com, you can follow along here. If you go to the cohort definitions page and search on the filter on the top right and search for the Graham paper, you get all sorts of cohorts there. You have 6 cohorts that represent your target cohort, your outcome cohort, and your comparator cohort. In this particular case, we have pre-specified this because this is not a tutorial on Atlas, but we wanted to show you the functionalities. So we have the target cohort. We defined dabigatran as the target cohort. For your comparator cohort, we have warfarin, and we have several outcomes that we have specified: the ischemic stroke, intracranial hemorrhage, and major gastrointestinal bleeding. For ischemic stroke, this is the current definition that we have deployed. So let's look at this definition. So you have here in the cohort entry events, which is the first section, certain things that has been selected. So if I were to build this up from scratch, right? If I was to build a cohort definition on the fly in front of you, I would probably do something like this. I would go to Atlas, and I would load the cohort definition page. I would go to new cohort. I would call this new cohort Odyssey ecosystem tutorial live cohort build. Outcome ischemic stroke, and then first thing I would do is I would say, can somebody give me the code sets for ischemic stroke? Can somebody give me the ICD-9 codes, ICD-10 codes, NOMED codes for ischemic stroke? We have from Graham's paper here some ICD-9 codes, but as we saw in the vocabulary demo, there is a way to capture this information in Atlas using concept sets. So I would, as my first step, build a concept set. I build a concept set for ischemic stroke. So okay, there is no concept set, so I'm going to build it. And I would search for so later today, you'll all have an opportunity to build your own cohorts, to conduct your own studies. So this is the user interface that you will go through to build your cohorts. Okay. Ten, 9, 8. All right, let's assume that we got this return.
Going through a talk.
That's probably it.
There are like 20 people ahead of you in line.
All right. So in this pre-generated cohort, there was already a concept set. The concept set included these concept codes that were pre-selected. It went through the descendants have been selected, just like Patrick had done in the morning. So once this has been pre-specified, it's imported into this cohort definition, and there's a UI that I wanted to show you of how to import concept sets from the concept set section of Atlas into the cohort definition section of Atlas. So let's assume that that has been done, and now you have concept sets inside the cohort definition page of Atlas. So this is ischemic stroke here as an imported concept set inside Atlas. So now, as part of this cohort build process, the first thing I would do is I would say I want a condition occurrence. So this is this top button here is something I would use to say condition occurrence. Inside condition occurrence, this section here, right now it says any condition, but I want ischemic stroke. So I would go and select, and I would import concept set saying ischemic stroke. I would import it, and there is ischemic stroke. The actual codes that go behind it is here in this particular page. So this is my reference library. Now, now, just having the diagnosis is not sufficient. I would, as the domain expert, as a scientist, I would like to restrict it to an inpatient stay. So I want to identify people who, in my data set, had ischemic stroke in an inpatient setting. So to do that, I have another option here called condition type. So I will go down here and select condition type. In the common data model, a type concept represents the provenance of the data. So where did the data come from? So if you want to know if this data came from an inpatient setting, then you go to the condition type. If you wanted to know if it came from an outpatient setting, you would go to condition type, or a visit type, and so on. So I would go here and then search for inpatient, and if it was fast, it would usually come. Let's say this is it. So I would go and select the ones that says inpatient, inpatient primary, inpatient primary condition, and so on. These are the different parameters I would select from that UI and go through this process of construction. and save it. And this would be my fully specified ischemic stroke definition. Once you have specified it through the user interface, Atlas has some built-in documentation in a human-readable fashion. So it will take those user interface and then say, in the initial event, people having any of the following: a condition occurrence of ischemic stroke with this type of type concept ID, this type of visit occurrence information. So this is how you build one cohort definition. If you would like, you can also have this cohort represented in many different ways. So you have a graphical view. You can get a JSON object, a fully specified JSON object that you can copy, and then you can take this JSON object and paste it in another instance of Atlas in some other people's site, and then the entire cohort definition will be reconstructed in that new instance of Atlas. Or you will also get your full SQL. So if you look at this SQL here, which is several lines long, all this SQL was written by Atlas. So you'll first may want to create a code set table. That code set table is based on your concept set. So Atlas will take the concept sets and create a code set table. It will then go through the different types of CDM tables and construct the cohort. So because we said we want people who had the ischemic stroke and is looking at condition occurrence table, it is creating this dynamic SQL that joins the condition occurrence to the visit occurrence to the observation period and so on to build the cohort for you. And once it's all done, you can press the generate button to the different data sources, and you will get your cohort. So it found 36,000 people who had the outcome. So the number of people in this 26 million or 23 million data set that had ischemic stroke were 36,000 people. So using this process, we can build more complex definitions. So in the Graham study, the target cohort was warfarin. The people who were on warfarin also had to have atrial fibrillation before they started warfarin. They should also have not had prior exposure to certain other drugs. So there is a set of inclusion criteria and exclusion criteria pre-specified in that document. So the way to translate that the cohort definition in the Graham paper to Atlas, this was the approach that was taken. Here is the entry events. So from the common data model, all the people who had the exposure to warfarin were first selected. We said, to translate that, we said it has to be on the first day in the person's history. It had to have started before, on or after October 19th, 2010. That was the cutoff in that paper. On the date that they got warfarin, they should have had at least an age of 65 years. They should have had a continuous observation in the data set starting at least 183 days, 6 months before their first dose of warfarin. These were some of the criteria that were pre-specified in that paper. There were some attrition criteria. They had to have atrial fibrillation. On the date that they started warfarin, they had to have a diagnosis of atrial fibrillation. So it says, with at least one condition occurrence of atrial fibrillation between all days before and 0 days after the exposure to warfarin. So that was the rule that was used. There was another specification in that paper. They should not be on the drug dabigatran. So we said if they were on dabigatran before they started warfarin, they should have been excluded. So it says, with exactly 0 occurrences of the drug dabigatran, starting all days before and 0 days after. Because if they had even 1 exposure of dabigatran, they would be excluded. And so on. So no prior treatment, not in a skilled nursing facility. So there was a rule in that paper that said they should not have been received care in a skilled nursing home. They should not have had a mitral valve disease. They should not have had a history of deep vein thrombosis. They should not have had a major joint surgery in the past 6 months. So all of these complex rules has been specified into the inclusion criteria of ATLAS. There was a criteria to talk about persistence. What happens when somebody stops taking warfarin? You may want to take that into account because warfarin is a long-term drug. So if somebody stops taking warfarin, you want to maybe stop them from the study, withdraw them from the study. So that criteria has also been incorporated. There were several censoring events. If they got a new exposure to dabigatran or apixaban or rivaroxaban, all of these were considered exclusions, or all of these were considered censoring or cohort exit events. They're all specified. Once that was done, this study was run inside the CDM of 23 million people, and it created a report. So here you will see an attrition view. There were 3,943 people who met all the criteria, but there were some people that met some criteria and others did not meet criteria. So if you look at the attrition view, you can see how people get dropped based on different types of rules. If you had the rule that seems to have taken the most out of here, it's probably one of these. So you can use this information to create your attrition diagram, which shows what was your starting population and how did you go down the chain to your study population. Now, once you have reached this stage, now you can start doing your study. Your first step is to create your table 1, your descriptive statistics. For each of your cohort, your target cohort, warfarin, your comparator cohort, dabigatran, or any of your outcome cohort, ischemic stroke, your cerebrovascular hemorrhage, all of these you can now create descriptive statistics if you would like, because each one of them is a cohort. And ATLAS has a way of doing it. So there is, in ATLAS, in the older version of ATLAS, there was a section called reporting, but it has now been changed. The new version of ATLAS is ATLAS version 2.6, has a new thing called cohort characterization. So I'm going to show you cohort characterization. Let's close this. Okay. So cohort characterization is a new functionality that was built, just released 2 days ago. I got to see it for the first time yesterday evening. So the idea behind cohort characterization is, can we to get all the different types of table 1 information, demographics, other comorbid conditions, the procedures, the other drugs that they're on, can we create a software to do it? In the past, what the ATLAS and OHDSI tools used to do was to look for the presence or absence of a code in the past certain period of time. So for example, you could say if there was a diagnosis of code for atrial fibrillation or chest pain in the 180 days prior to the cohort start date. But in the new cohort characterization, you can say, I want to define my table 1 as follows. I want to define ischemic stroke history as presence of 2 diagnoses in the primary position in the inpatient stay. So I could actually build a table 1 that contains more complex information. So it's not just the presence or absence of a code, but now I can specify a complex sort of presence of a code in a certain place of service with at least 2 times in X amount of time, and so on. So wish we can show that. Okay.
It's not you, it's the internet.
I know. All right, so I've got some that's already pulled up here. So they're going a little bit ahead. This one is pulled already. So let's pause about the Graham study. Let's talk about the other types of cohort characterization for a second. So recently we started supporting health economic analysis. So maybe we want to build a cohort and characterize their financial information, right? That's a use case because that's part of health economic analysis. As a health insurance company, I work for a health insurance company, and we want to know for our client, the account that we sold, what is their per member per month cost? What was their admits per thousand? What was their what is the most expensive drug that the population financed? So here is an example of Atlas actually doing health economic analysis. So this is running for Medicare members. Also, all of this is synthetic data. And here you can see that Atlas has calculated for a cohort of Medicare members, there were 26,000 people. It said there were 1.3 million claims with certain per thousand metrics. So 51,000 claims per 1,000 people per financial year. Their total allowed amount, contractually allowed amount, was 291 million. Their per member per month rate was $924. Their paid was $198 million, and their paid PMPM was 630. And it gives you certain metrics about allowed to charged, paid to allowed, to understand network discounts. You may want to know trends. You may want to know if which month had the highest rate. Maybe there was a particular month there was a huge spike in your financial information. So this Atlas allows you to do that, and if it works, there you go. So there is a raw table and the visualization piece. So every metric, it has rendered it to show the trends. PMPM was $660, went down to $631, went to $649, and it looks like there is a PMPM paid amount trend that is going down, which is an important piece of information if you're an actuary. So this is an example how Atlas is supporting actuarial analysis. If you want to get your trends on a weekly basis, sure, if the internet works, it will show you. It did, yay. So now you have the same one in more granularity. So your allowed PMPM trends are this way, progressively going down over the calendar year. So this is an example of Atlas characterizing the financial information of a cohort. You may want to characterize drug utilization. In this framework, in the health economic framework, cohort characterization can be done at baseline or during the cohort period. So if you think about the Graham study, cohort characterization is done at baseline. So at the date that they became the target cohort, or at the date that they became the comparator cohort, the cohort start date, what were the baseline characteristics? We want to know the baseline characteristics so that we can adjust them as confounders when we estimate the outcome. But in health economic analysis, you want to know what is happening during the at-risk period. So if the cohort period is from January 1st of 2018 to December 31st of 2018, which is the use case of a health insurance company, then during that at-risk period, what was the financial health economic characteristics? What was the utilization of care? So we have built here cohort characterization during the cohort period or cohort characterization during the baseline period. And the baseline period was defined as the 365 days prior to cohort start date. So here, maybe if you want to know the drugs. So every drug that the cohort, there was a claim for, is now characterized in this tool. Let's go back. This is still loading. I think you guys are are out of luck to look at the new and the coolest cohort characterization functionality of Atlas. So I'm so sorry about that. Do we have screenshots? You saw some screenshots in the morning from Patrick's. Let's see. There you go. Okay, so this is a new functionality that just got released in 2.6. So what is this functionality? It allows you to select the characteristics that you want described. So you can go and there is a demographic section in the UI that now you're all imagining with me because I've seen it for the first time yesterday. So there is a demographic section that allows you to select age or age as a continuous variable, age as a group, 0 to 5, 5 to 10, 10 to 20, and so on. Or you can select conditions, comorbid conditions. You can say, I want to find out all the conditions that the person had in the 180 days prior to cohort start date, or all the conditions that the person had in the 365 days prior. Or I can customize it and say, I want to do it for 45 days because I'm just curious about 45 days prior. That's my use case. So you can specify those and make changes in the UI, and Atlas will support those. So you can build rules to characterize a cohort. You can build a rule around drugs. You can build a rule around procedures. You can build a rule around a combination of drugs and procedures. In fact, if you go and look at Pavel's comment, Pavel is one of the developers who built it on GitHub. He said, go crazy, put your own SQL into it. So you can write your own SQL statement and save it inside Atlas, and it will compute that as a characteristic for you. So once you get that information, it will do calculation of continuous variables or categorical variables, including especially binary outcomes like yes or no. So once you get that, you can now say in this group, my target group, the number of people who have this comorbidity is 30%. In my outcome group, it is 35%. So you can now compare the two. So here in this slide, you can see that the age group 65 to 69 is 15.5% in the warfarin group, while the other group has 16.6%. So the graph here has an x-axis and a y-axis, and it shows you each dot is each characteristic. The y-axis goes from 0 to 100. The x-axis goes from 0 to 100. So if it is 35% on this cohort on the y-axis and 30% on the x-axis, you will get a dot that is the intersection of 35 and 30. Now, if both of them were 35, it would be right in the middle. If one of them is 45 and other one is 20, you would start getting outliers. And the outliers is what you want to look for. So this graph from Atlas will immediately give you insight on what is not evenly distributed between the two cohorts. And imagine doing this for every possible type of concept that is captured in the CDM. Drugs, procedures, conditions. So this is a new functionality, a very powerful functionality inside the atlas, which you cannot see right now. And I think that should complete what I wanted to say. Any questions? Go ahead.
So with the option for baseline and the cohort period, is the difference with respect to the timeline or the study period only, or if you were to look at drug utilization during baseline versus drug utilization during cohort period, is the timeline only different, or do you include cohort-specific characteristics as well?
I'm trying to understand your question.
So, like you had done it for warfarin, there are some exclusion and inclusion criteria. So, when you're looking at drug utilization for cohort period, does that include all those inclusion and exclusion criteria, or is it just specific for the time period compared to the baseline?
It is. So I think the question is, does that? No, let me try to answer your question straight. The cohort is built by using all the inclusion and exclusion criteria. Once the cohort has been built, you get a cohort table that has a person ID, a start date, and an end date. Now, if you want to do baseline characterization from that cohort table, imagine Atlas only using person ID and start date and looking at information from the CDM prior to the start date. But if you're looking for the option of during the study period, which is start date to end date, then Atlas will look at the period between and look at the CDM for information for the person during the start date and end date. So it's a temporal query.
Okay, okay. And then when you ask for the drug utilization, does it display the different drugs, the names of the drugs which they used?
Yes. So the question is, does the tables and the graphs in the Atlas characterization UI show every drug that is being reported on? So if we could, one of the things that we would have shown you is 15,000 drugs have been computed. So the table in the UI of Atlas would show you all 15,000 drugs that's available inside the CDM.
So as part of the BEST initiative, we had a chance to look into Atlas. How is characterization different from patient profiles option that you have? Because that shows everything during the baseline as well as the period.
Right, okay. So the question is, there is a functionality in Atlas called patient profiles, and there's a functionality called cohort characterization. Patient profile or person profile is profiling one person. Cohort characterization is characterizing the entire cohort, which may have more than one person. So, so for example, if you take diabetes, for person profile, it will say if that person has diabetes or not. In cohort characterization, it will say 35% of the cohort will have diabetes mellitus. So that's the difference between the two. They follow the same idea of running a query for the concept for either one person or for the entire cohort.
I think this is more kind of a comment, not necessarily a question. I think when you talk about you don't have exclusion, just inclusion, actually you do, you just inclusion the zero of that. But I think inclusion exclusion is a very mature concept in clinical research. I don't understand why you don't use it here for the cohort build out.
Yeah.
I would do that.
Yeah, absolutely. So the comment is about the inclusion criteria and exclusion criteria. It was a deliberate choice of words to say exclusion is actually inclusion zero. So it's, which is exclusion. So effectively it is, the reason is when you translate some of these into English language, it can be a double negative. So should not have myocardial infarction. Can you give an example of a double negative in this particular context?
So it'd be like, well, it's a not, right? So
Right.
you would put two ways of saying myocardial infarction and somehow contradict yourself in the same. It's like, does your parentheses close or is it open? And if not, is it a...
So if you say we should exclude the people who have not had myocardial infarction, right? Excluding people who have not had myocardial infarction means take out people who have not had myocardial infarction, a negative of a negative, which means keep the people who have had myocardial
Yes,
infarction.
that's what it is.
And so so it's when you start from translating human language to computer language, it starts getting confusing. And to avoid that ambiguity, this rule was made.
But if you have a compelling use case that you really want to champion, we welcome dissonance. I think that's what Patrick would say.
There's a question in the back there.
My question is around health economics. When you do health economics studies, there are various techniques you have to follow. Risk stratification, either you're calculating mortality rate or readmission or length of stay and things like that, because that's the moving from fee-for-service to value-based care, right? And then this particular cohort definition, do you include like DRG codes or John Hopkins conditional category codes, where you risk stratify a particular condition, and then based on the severity, this falls in this bucket?
Mm-hmm. So the question is around using stratification based on certain types of information. That information can come from the DRG codes. The information can come from the DXCG or those codes, so type of risk, personal level risk computation, right? Absolutely. If you have data that has been ETL'd into the OMOP common data model, and that is available as a concept, you can use it to build a cohort that is either high risk, medium risk, or low risk based on the different types of scores that you have. You can use scores that you feed into the common data model, or in the next tutorial, you will see person level predictions. So you can build prediction algorithms using Atlas itself and score each person. And you can use that score to stratify people into high, medium, and low risk. And each one of those is now a cohort by itself. A high-risk cohort, a medium-risk cohort, and a low-risk cohort. And then you can characterize those cohorts, whether it is for comorbid conditions, drug exposure, or financial information, and then say, does the high-risk cohort have higher cost compared to the low-risk cohort? So yes, absolutely possible within the framework. It is still a developing capability inside Atlas, because the CDM6 was the first time that cost came into the picture.
That's great. I have one more question on patient level study, right? Patient, not population, patient level. When you do a patient level study, the predictive analytics, you can predict the patient is going to get diabetes, like Bang model, or a heart attack using Fermion model. There are several models too. But the problem is, say for example, you take blood pressure reading, diastolic, systolic. It falls into three categories, right? High, medium, and low. So you need to create your variables accordingly, right? It's just not a variable. You talked about continuous variable and then input and output parameters. So does the cohort definition tool under Atlas give me the ability to go into a variable and do like a high, low, medium, things like that? Why I do that? Because if I want to get into a causation, this caused this. So I need.
Can you give me an example, and maybe we can talk about Atlas as a solution for that?
I'll just start talking about. I'm predicting this person is going to get a heart attack.
Uh-huh.
So I'm going to predict this person is going to get a heart attack. The BMI, age, is diastolic, systolic, like 5 parameters, right? You take the 5 parameters. But the point is, these are the 5 data elements, but I cannot do a causation study. This 5 parameters based on A, B, C condition, logic will get out of that, right? If I want to do that, I need to break these variables into multiple variables, like blood pressure into high blood pressure, low blood pressure, right? I need to categorize that.
Right.
So I need to categorize it because people have low BP,
I see.
high BP, and
I
things
see.
like that.
So
every variable, when I want to go into a patient level study, I need to take that into break it down. Then only I can get into a predictive analytics.
yeah, I think I understand what you're talking about. So if you want to build a prediction algorithm of diabetes inpatient admission, let's say among the people who are diabetic today, who are going to be admitted to the hospital in the next 1 year, for these, you want to provide the learning algorithm, some maybe lasso logistic or maybe some more complex machine learning model that you want to provide it with covariates that it can learn from. So those covariates could be based on demographics, could be based on BMI and things like that, right? So you may want to use BMI as a continuous variable. You may want to use BMI as a categorical variable or an ordinal variable. You may want to even want to use financial information from history. So all of these are characteristics, covariates, that can be used by the learning algorithm. So one of the things that Atlas is trying to do and has achieved good success is to build custom characterization. So the tool that we are supposed to demo is to show you that you can select from pre-configured characteristics, or you can modify those and build your own, or if you want to go crazy, you can write your own SQL and publish it as a characteristic. So you have all various types of options to characterize. So if you want to classify BMI into 100 ordinal levels, you can. Or if you want to divide it into 3, you can. Or if you want to use it as a continuous field, you can. So all of these are options. What has not been achieved yet is to make that available to the R package. And I think that's the future next step that we want to do. So right now, we can achieve custom characterizations using the Cohort Characterization framework. But the next step, would be to make that available to the R package to do learning.
Thank you. When you were doing, I thought that characterization will answer that mail, because even you can do core morbidities as well.
Yeah, this is where we need to all work together, and that'll be the
That's
fantastic.
Most important tool in case of that. Thank you.
That just came out like yesterday. Thank you.
So before we move on, why don't we all stand up? No, seriously. Let's take an energy break, shake it out. Come on, indulge me. I'm an epidemiologist. I know you're too sedentary. I've seen the statistics. Not you personally, but you as a population. Just shake it out. And then you can sit down on your own free will. But everyone's looking a little fatigued, and you might have figured out the secret. This is a marathon, not a sprint. And as a 4-time marathon runner, I can tell you training is everything. So don't worry, it gets easier as you get into this. It is like drinking from a fire hose. There's going to be a lot of information today that you haven't digested yet. And I know that it's going to be tough to take this all in. So as we are settling back into our seats, I promise you'll get a formal break soon. And this is going to be quick and hopefully fun. How many of you in the room are epidemiologists, for a show of hands? Or I self-identify as an epidemiologist. You don't have to tell me if you're a real epidemiologist. Good. Okay, so you can fact check me if I make any ridiculous statements about exposures and outcomes. I'm going to pull up Patrick's framework. But this gets easier, I promise. Although I feel like I'm losing my audience by encouraging you to stand up, but you can sit back down. But we're going to do a quick discussion around incidence rates. I promise you this won't be... Is this the display rate? Good. This will go fairly quickly, and then, I don't know, maybe we have cookies or something out there. Maura always surprises us with snacks. She's great. So let's go back to our favorite thing, and this might not be the right way to view this. Senna, what setting on your laptop shows better? Can't quite see it. Well, you can see, this is supposed to say dissecting the anatomy of incidence. This should look like our bread and butter, because this is kind of how we think, right? We have time at risk. We've been talking a lot about the cohort entry and the cohort exit, and we are looking for some occurrence of something we're defining as an outcome. We can be pretty broad with how we define an outcome, but we are not going to be super broad with how we are defining our incidence proportion. We are going to be looking for our favorite target cohort, and we're going to be looking for the number of persons who have that new outcome occurrence during the time at risk. And then we're going to make sure we create the denominator of out of people who are in there who are within the time at risk but don't have the outcome. So Why am I showing you this? Because these fractions should be how you think about how we're going to put these building blocks together. You saw those Legos earlier, the T, C, and O. If you ever participate in a workshop with us, T, C, and O are going to become the things I'm just going to rapid fire ask you questions. What's the T? What's the C? What's the O? But what you need to know is how to put them in order. And that's why we have these beautiful color-coded things, and you can't even see the bottom part. Even better. What the bottom fraction is obviously the incidence rate, the number of persons in the target cohort who have the new outcome occurrence during the time at risk divided by the person time at risk for persons in the target cohort with the time at risk. And it's difficult. This is actually really not the world's easiest thing to put together. We joke about it, but there's a lot of questions that go in here. Who is the target? How should I define the outcome? What is time at risk? How do I account for patients with incomplete follow-up? A huge problem in our real-world data sets. I'm not even going to skim the surface on that one. I'm just going to say that's a tough one in itself. And you know, what metrics should be reported and what data should we be using? And I'm going to pull the slides back and just show you on the screen so you can actually see this. This is falling off the screen. So let's see. We have to make a simple answer out of all of this, and I guess you can kind of see the bottom. We need to look at time at risk, and we have to figure out that window within the start, what comes after it, the on treatment, the intent to treat. We have so many decisions we're going to be making, and wouldn't it be great if we had a tool that helped us do that quickly? Good news, we do. But these are going to be something I want you to frame your reference in this timeline idea because it's how Atlas thinks too. It's going to ask you quite explicitly to input your parameters. So, you know, what is your T? That's your target, right? What is your O? And what's your time at risk and your stratification criteria? Just to go back to the question that was asked earlier, we're going to be very basic in our stratification here. We're not going into huge risk stratification engines or anything like that, just to anchor it in the complexity of what we're going to do. But because we have this amazing tool, let's test drive it. Let's play around with incidence rates. I've made a couple of cohorts here. So prior to getting to this point, what have you been doing all day? You have been getting familiar with the concept sets. You've been learning a little bit about how these concepts come together and you can use them in a cohort definition. And you've also been figuring out ways to create different types of cohort definitions. Maybe they're your target. Maybe they're your comparator. Maybe they're your outcome cohort. We feel pretty good about that. Show of hands. We feel like we sort of understand the building blocks. You don't always have to show your hands, but it makes me feel like you're engaged if you move your hands. So we have building blocks, right? We have this idea of pieces. And we're getting to the piece now where we're taking those things together and actually making something with this recipe. So on the left, I have the ability to add target cohorts. This is where I would choose from all these beautiful cohort definitions I've created, who I'm looking for, who I'm comparing against, and in this case, we're looking at new warfarin users without prior AFib, and there's another cohort, or that's the comparator, and the target cohort is digoxin new users with prior AFib. And I want to look for the outcome of a couple ways to look at bleeding. As we were talking about earlier, bleeding is by itself quite a big bucket. It's, dare I say, quite messy, and it hemorrhages details. Okay, so you're tired of my sense of humor. It's okay. Hang in there. I swear there's probably cookies later. But you can define many different types of outcomes here. You can be greedy in this particular tool because all you're doing is going to be beginning to ask it to just play with different configurations of your numerator and denominator. So you notice here I have 3 different outcomes definitions in here. I'm not going to ask Chris Knoll what the maximum is, but I'm going to assume it's like maybe limited to the size of your screen, maybe how much compute you have. But you could have a lot of these here. You could have quite a fun little group of 7 or 8 things you're competing with and trying to figure out the best definition. And your time at risk window here is an interactive section where we're just going to set that window we were just talking about. So I'm going to have it start with +1 days and end a year after. And you can configure this. You could be explicit with the end period. This is really at your discretion. Yes?
Are these 2 things at the top, is that the numerator
Yes. Yeah. So yes, I'm going to say yes, but because I'll show you in a second, you can actually, yes, we're putting in parameters so it can crunch them. And then in the next generation screen, we're actually going to select which one we want to view at a time. So you can play around with the who's in the numerator and who's in the denominator. But simply yes.
Okay.
Yes, and I guess is the answer. Any other questions?
Well,
Yeah.
to Kristen's earlier slide, though, it's not just numerator and denominator.
Right.
Because questions will arise like, what do you do about a person who's in your target cohort who previously had the outcome? And in which case, that person should not belong to the people at risk.
Exactly.
So you actually really need to not think about this as what are the numbers that are the numerator and the denominator. Rather think about it as what are the cohorts or the populations that you are trying to generate statistics about.
It's a good point. And I take it for granted that that assumption is understood. But if this doesn't make sense and you don't want to admit it, that's okay. We can chat about it after. It's just thinking very deliberately because Atlas is looking for the expression in a very specific way. But we are going to play around with the study time at risk. We've left it here to be about a year. And the stratification criteria is really the unique subgroups. So you could add criteria based off of other covariates that you have at your disposal. You could add an age criteria. So I'm going to pop this up just to show you. I could add, let's say I was going to add the age. I already have an age one, but I just want to show you your options. You can basically pull from whatever is at your heart's content that's available to you. So I have V6 in here, so I actually have quite a bit more options than the average bear. But if I wanted to create a stratification criteria based off of data I had available to me, that's really what this is for. This is to create those substratum so you can look at deviations of rates. And you'll see in a minute why that's important, but suffice it to say it's allowing you to create sub-buckets on that fly, and then you can then see how that affects your totals on the next screen. I'm going to pause there for a second. Are people tracking? I see some questions.
For time at risk starts with start date plus 1 day. What's the start date?
So let me pull up this.
Is it the start date for one of the cohort definitions?
Yeah, let me pull this because I think this timeline helps. So when we think of start date, your time at risk window, so we're looking at the possibility of values of people once you've set up your cohort entry and cohort exit, the possibility of calendar days, however you quantify them in that time period. And I'm just going to go back.
Because you have multiple cohorts there.
Right, so you're going to have to think, this is why you have to really think about who are you looking for, who are you looking to compare to, and then you're creating your rule kind of based off of looking for the T and the C and knowing the O that you're looking for. What is the right window to capture for that? So not every O needs a huge window. Some can be quite small because they're acute and they happen very quickly. Some we know have it's a latent exposure. So I'm not going to give a hard or fast rule, but that is kind of one of the burdens of navigating this is having the acumen or the group of folks to help kind of wrestle that. How do you set the green window inside the blue window? And I know, Sana, you wrestle these a lot. Any advice from the battleground?
So if you switch back to Atlas real quick. So we have 2 target cohorts, and we have 3 outcome cohorts. So you're actually going to generate 6 separate rings.
Yeah.
So each T is going to be evaluated for each O in the time at risk window that you've defined. And so even though you're able to add multiple here, you're still evaluating each one on its own.
Okay.
Yeah.
And to your other question about the risk window itself, it's going to be based off of the cohort start date for each of these cohorts. So if we take, what do we have up here?
We have
using the dapigatran exposure, so it's the first exposure in a person's history, and we start the risk window at day 1. That's going to be the first day after they started dapigatran until 365 days later.
And so your rates, I'm still thinking in terms of numerator and denominator, and so I'm having trouble
I'm with him on that.
I think we should step through this and see what.
Yeah, it gets a little clearer when you see the generation screen why it isn't, it's close to what you're thinking, but it's not quite there. And I'm not trying to say like there's amazing things behind the curtain, but like I think I got it more once I kind of saw value start to be generated, because my world was historically just numerator denominator. But before we move on, assuming we're going to come back to this point of kind of how these T and O's relate to each other, are there other questions before we get to the, let's look at against data? Anything conceptually about this screen that's troubling and folks want to go through? Yep.
I'm not sure if I should ask this now, but I'm going back to my statistics class in college, and what kinds of statistics, what kind of things that we're actually going to use to compare, and what statistical methods are we going to use. Basically, I'm expecting each outcome to give you like a single number. Is that what we're looking for in the end? Is our cohort really just telling us? I'm sorry, I can't really read the screen; it's too small. But is it really telling us? Is each cohort like patients who are taking warfarin, or actually is one of the numbers like incidences of stroke in the treatment period, and that's one of our numbers?
Yeah, so while this is running, let's talk it through, right? So our outcomes, there's 3 of them. They're basically different ways to say bleeding as an endpoint. We have one outcome that is incident ischemic stroke. We have one outcome that is incident intracranial hemorrhage, and we have another one that's GI bleeding, right? So you'll have calculations for the rate that in the target group or in the comparator, whichever one you select, based off of the window that you've set out, based off of that exposure, the incidence of that specific definition of bleeding relative to the window you've set. If that's not generic enough, but.
So this is going back to the previous lecture about the definition of cohort and defining cohorts, less as a statistician, more of a different definition. But again, I'm sort of thinking you have to have a study group, and one of the rules that I've learned is that you could never ever change your study group because you're going. If you change your study group, it means you're playing with the data. You're trying to extrapolate something that doesn't exist. So I'm sort of not clear about the concept of multiple cohorts, and why can't we have a single cohort and we're just applying like a before and after kind of numbers. And maybe this is me remembering stuff 15 years ago that doesn't make any sense anymore.
Trying to think of the right way to repeat your question back to you, make sure I've got that. So you're kind of asking about so we're looking at multiple things simultaneously.
Yes,
it's a little
exactly.
confusing. How are these things coming together? And so I guess I'll start with answering the first part, which is by design, Atlas is supposed to be the ability to test perhaps multiple definitions concurrently, or maybe you have multiple endpoints you're looking at, and it is designed to help you keep that in the workflow. You can do multiple things at once, right? But there really is one target group who you're looking at. That's cis-digoxin new users with prior AFib. And you can assume, like Gotham showed you, I built a cohort, and I included a certain concept set for digoxin, for AFib, and I set the exposure period for that. And then I created another cohort for warfarin new users who had prior AFib, and that's the comparator to those people. And then I built those definitions for the outcomes. And now all I'm doing is, when I'm generating these statistics, is really looking at, based off of that target group, and these 3 ways I could say that bleeding is an outcome, the incidence of those different types of bleeding. Maybe because I'm working with other investigators who truly do not agree that these types of bleeding are equal, and they want to see the different level, like that, those 3 types of things, even though they're kind of, in a lot of minds, the same thing, they're not, right? So it's giving the transparency of the incidence rate relative to each nuanced definition, and just doing that in one fly versus running it everything like one after the other. It's just, it's kind of like parallelization basically, and I am deeply regretting accidentally hitting generate cohort, but good news, there's some statistics for you. So what am I looking at, right? I told you that when you get your results, so like Senna said, you will then pick which definition you want to look at. So I'm actually looking at the comparator, but I could switch to the target. So now I can go and expose, having asked it to crunch many things simultaneously, I'm now going to scrutinize each calculation individually. So let's just look at, actually this one's a little easier to read, the comparator. So among people who received or for new users with prior AFib, and I believe we constructed this window, we said it was first exposure of new drug or something like that. I kind of always talk myself in circles saying this in plain English, but we've created that cohort, and we said we wanted to look for, in this case, incident ischemic stroke. We can then scrutinize the proportion, the time at risk, and the rate relative to, in this case, we have both before we stratify and then stratified by those parameters we set up as additional covariates of interest. And some of you might say, and I'm going to zoom this out just because it's a little harder to see. So why is there this giant black box? Well, it means there's actually not a lot of deviation in the rate in the sample data I have. It's a small data set. So I actually only have, let's say, one case that is female and has heart failure. I have nobody who's greater than or equal to 75. So some of my stratum then have restricted this to be just too small an N, basically. But the blue that I do see is this the rate of 26.32 cases per year. So 2 criteria passed, 1 criteria failed. There are 478 people who, if I remove that criteria, I think this is how I would interpret this, basically is giving you scrutiny into your feasibility of your definition at this point. And why would this be important? Because very regularly we create incidence rates with additional substratum that may not be feasibly available to create that calculation. And so exposing it at each level gives you the idea to figure out what you could or could not relax. And you might see variation across endpoints. So maybe intracranial is better. Actually, intracranial is worse. I have SimPuff in here, so it's not the world's best data set to find this, but you could suffice it to say, and I'm going to pull up just some screenshots of what this could look like. You might find some good insight where you can adjust how you're thinking about that outcome. Sorry. So let's see if this is bigger. You guys see that? Where I could actually play around with, I have much bigger sample sizes, but I see that when I combine a gender and age criterion, I suddenly lose, 51 people or something. So the purpose of this is really to give you the idea of seeing the different ways you can pivot your particular T, C, and O into this calculation. And my humble opinion is it's a beautiful and elegant way of having traceability in your calculations, of sharing these definitions, and figuring out the optimal concept set for that analysis. So I'm hoping, I feel like everyone's kind of lost in the wilderness and you're afraid to send up a smoke signal, but so here's the summary. You've watched a machine quickly pull a target and an outcome cohort, define a time at risk, and then calculate the incidence rate for that outcome for that target cohort. That was in, just a matter of minutes. I did the same thing for a comparator cohort for the same outcome in the same relative time at risk, and I could visualize that. And I could run that to my heart's delight on the data that I have. I could play around with different stratum. And that, to me, technology aside, and the fact that demo data is still pretty darn cool, right?
That demo data, is that part of the Atlas ecosystem or is it a separate project?
Yeah, no, well, the SimPuff data is actually separate to OHDSI. It's just its own thing. But people have been generous to release CDM converted SimPuff data. I believe Erica's releases came out a month.
So I might be asking about the data itself. Is it open source or is it, yeah, okay.
Yep.
All right, it's called SimPuff?
CMS SimPuff, yep. And there's on the,
Spell it.
yeah.
Okay. SimPuff, P-U-B.
Yeah. But what some generous folks have done is actually load it into the CDM so you can play with it and play with the tools before you even have your own CDM conversions done, which is also really cool. Thanks, Erica. She's not in this room, but she's over there. So yeah, question back there.
So this web-based application, the data's sitting there, and I can play with it until my heart's still up. Is that true?
That is a true statement. The one that we're using today, that awesome, so the question is it web-based system, can you play with your heart's content? Yes, and there's a couple iterations of that are out there. So on the OHDSI website, there is the Atlas instance there. That's free to your heart's content. Lee Evans helps us maintain that. The one for today's environment is provisioned through James's project to make it easier to get all of this on AWS. So he did the same thing, just in a parallel world. So yes, there are public instances of this available for playing. And hopefully in the future, we might convince somebody to give us better data than fake data. But hey, dream big, right? So, and I believe the new packages that have been released, Sunik can confirm this, I believe there's an effort to make sure that as these new packages that we said were just released, as they become available, the public version also reflects that. But I can't speak to the how the lag between when a new package is released and when it's in the public one. It's not long, though, I don't think. I don't know. I'm looking at you, Senate, to confirm or deny. The question was, I said, so for the public instance, when new packages are released, sometimes there's a little bit of a lag to get the new package into the public, like Atlas, or sometimes that window is a little bit longer, but it's not that long.
Yeah, it usually just varies based on what's been done, kind of space time they
Be good? We feeling good about instance rates? Maybe not. It's okay.
So I was just going to add to this overview with the statistics that you see up on the screen, and albeit in the back, it may be a little hard to see the slides. One of the things that we utilize this tool for as we're constructing studies is to just understand if any of the people in our target or comparator groups have the outcome of interest that we want to study. And so what you are seeing on the screen here is that we have presumably either the warfarin or the dabigatran, cohort on the left, and that has about 19,000 people. And on the right-hand side in that drop-down, we probably have like ischemic stroke or one of the bleeding events. And you can see that there are about 201 cases. So we can detect that some people will have that outcome in the time at risk. And the stratum below it is basically just further filtering that 19,000 people down to 10,000 male. And of those 10,000 males, there's 99 cases of presumably one of the bleeding events. And so this is at least give us some indication that we can conduct a study that's going to at least detect one of these outcomes in these groups. And so when we do that with a list of targets and a list of outcomes, it's a efficient way of evaluating each one of those sets of questions that we want to ask. So this isn't a causal inference, because I'm going to talk about that in a little bit after a break, but this is at least a way to get a sense of the proportion and rate of the events in the populations that we want to study. So.
Yep. So I'm wondering if about how you define time at risk. Like, say someone's in the target cohort for only a month, but the time at risk is in a year after their start date. So is it the intersection there? So they would only have not contribute time. Their time at risk would only be the intersection of where we define time at risk here and the target cohort. All right.
So if so the question is, if we have a person, a member of one of the cohorts, let's use dabigatran, and we only have 30 days of time that we can observe them, but we're looking in a 365-day window. I believe that they will contribute to the 30 days that they have in that cohort, and if they experience the event that we're trying to detect, they will be counted as a case.
Or if you have like 30 days and then they're out of the cohort for a while and they're back in.
So that goes to your cohort definition. So if you wanted to, I think the default behavior is going to be at the end of their observation. if they disappear and then they come back into the database, we won't immediately pick up their next observational period as a continuation of the time at risk. Basically, when you disappear, we stop.
Yeah. And there are a lot more functionalities around censoring and things like that that I haven't shown you, that if you start to play with it, you'll notice that I've kind of just breezed through them because when you have questions like that, it becomes quite relevant in general. I think, you kind of get the idea of applying additional criterion, but exactly. And as you begin to get more familiar with the way we construct the observation period and even things like drug era or condition era, you can get more sophisticated with how you begin to construct those fragmented views of the same person.
Are there any other questions? Otherwise, we're going to take a quick 10-minute break.
Everyone's like, no way, I'm not going to stand between the break. Well, thank you guys. Let's go get some coffee and cookies, re-energize, and then we're gonna run a study. No hype or anything.